Mercury orbits in a gravitational furnace, enduring solar radiation that should have left it a barren, static ruin billions of years ago. It is the smallest planet in our solar system, trapped just 58 million kilometers away from the sun's surface. This data visualization shows the result of that proximity. The sun-facing side spikes to a boiling 430 degrees Celsius, but at night, the surface temperature plummets to a freezing minus 180 degrees. When we added Venus to this chart, the difference is clear. Venus has a thick, heat-trapping atmosphere that keeps its temperatures relatively stable. Mercury has almost no atmosphere at all, meaning there is nothing to insulate the planet once the sun sets. Because Mercury sits almost perfectly upright on its axis, it has no seasons. The deep craters at its poles never see direct sunlight, remaining in permanent shadow. Even with boiling temperatures right next door, radar data shows these dark pockets harbor massive deposits of frozen water ice. For decades, these environmental contrasts led planetary scientists to characterize Mercury as a static, frozen and fried rock. That was the consensus, until they looked inside. To understand this planet, we have to look past the surface and examine its internal anatomy. Earth's core takes up 15% of its volume, while Mercury's iron core accounts for a staggering 60%. This oversized core gives Mercury the second highest density in the solar system, suggesting a history far more complex than simple cooling. One leading theory is that early in the solar system, Mercury was once much larger. A glancing collision with a massive celestial body could have stripped away the outer crust, leaving only the dense iron center behind. Alternatively, intense solar radiation from the young sun may have baked the outer rock layers until they boiled off and vaporized into space. Whether the crust was smashed off by an impact or boiled away by radiation, this oversized core points to a history defined by chaos, forcing a reassessment of its nature. While its formation was violent, new analysis of mission data reveals this activity continues today. Researchers led by Dr. Valentin Bickel used machine learning to analyze 100,000 high-resolution images taken by NASA's MESSENGER probe during its 4-year orbit. Hidden in that data were roughly 400 bright linear features, appearing like fresh streaks on the sun-facing slopes of young impact craters. In this geological cross-section, meteorite impacts create deep structural fissures, reaching into the subsurface crust. Volatile materials, like sulfur, use these cracks to vent upward. When intense solar radiation hits these sun-facing vents, the materials outgas into space, leaving bright chemical streaks behind. This active venting confirms that Mercury's interior is still under pressure. It replaces the image of a dead rock with that of a world responding to its environment in real time. This evidence demands we view Mercury as a dynamic world, one capable of generating magnetic tornadoes and shifting its own surface features. To investigate these mysteries further, the European and Japanese space agencies launched the joint Bepi-Colombo mission, which will enter Mercury's orbit in November 2026. It utilizes a unique dual spacecraft configuration to simultaneously map the planet's magnetic environment and its deep interior structure. Data from this mission will allow researchers to establish a precise timeline for these outgassing streaks and clarify the origin of the giant iron core. Mercury has transitioned from a scorched relic into a specific case study of how rocky planets survive and evolve in the most extreme environments of the inner solar system.